Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, parsing a Boolean expression. The idea is that we're given some string that represents a Boolean expression, and we want to know whether it evaluates to false or true. The difficulty comes from the fact that it could be a highly nested Boolean expression. So just to give kind of the quick structure of this, they give us some information about it here. So the main base cases, of course, are if we're given like the character t, that represents true, and the character f, that represents false. So these are the simple cases. Now, it can get complex when you start to introduce parentheses around these, because then the order of evaluation becomes relevant. So for example, take parentheses and you add, let's say, the ampersand. So this is the logic and operator. And then within the parentheses, you're going to have these two characters possibly separated by comma. So you might have something like this, t, and then f. So it's not the way we would write code in Python or Java where you have like the t and then the ampersand and then false. I think you'd have double ampersand. It's not that way. It's actually a bit easier for us to parse this expression because the result of this is going to be all of these logic and. So if all of these are true, the result of this is going to be true. If at least one of them is false, the result is going to be false. And this could be arbitrarily long. So we could have a bunch of expressions and they're all going to be separated by commas. And now this is where things get interesting. These themselves could be expressions that we have to evaluate. Some of them could be and some of them might not be. For example, you might have a t here and then we want to logic and that with the result of this expression. And then here we could have another logic and then in here we could have a t and let's say a false. So the order of evaluation is going to be, of course, to know the result of this entire thing, we have to know this logic anded with this entire thing. But we don't know what this is. Is it true or is it false? So of course, we have to solve the subproblem first before we can solve the entire problem. So now you can see why this problem can be solved naturally with a recursive approach, because the subproblems are going to be solved the exact same way as the entire problem itself. Now let's think about all the different cases that we're going to have to deal with and then try to formulate a reasonable approach to solve the problem. We kind of have the base cases covered. That's the easy part, but let's think about all the different combinations we could have. So I kind of talked about the logic and case. I'm going to go now to the not case because I think that's actually the simplest one, because suppose you have something like this, you have the not, and then inside of here you have, let's say, t. So of course this itself is just going to be the opposite of what the inside happens to be. This is kind of a subproblem as well. So this evaluates to true, and then we get the result of that, and then we take this and we negate the result of that. So what we get is false. Now with the not, as it kind of shows you here, we're not going to have comma separated values like this because it doesn't really make sense. Not doesn't apply to a bunch, it applies to a single one. So that's why not is the easy case to handle. Whatever the result of this, which by the way, this is invalid. I hope you can see why this is invalid, what I just kind of mentioned. So, but we could have something like this. Let's say where you have ampersand and then you just have like a single expression here. So whatever this is, we take the negation of that. In either case, you can easily tell that to solve this entire thing, we would just pass this guy into the recursive call, and then whatever the result happens to be, we negate it. So this is an easy case to handle. It's very similar to the base cases, at least conceptually. When it comes to coding it up, there are a lot of ways to do it wrong. So that's what we'll be focusing on in this video, but there's a couple more things I wanted to mention before we get into the implementation details. So lastly, let's go over the third way. We talked about and not. We also have or, which is going to be with this character. I actually don't even know what this is called. So this character, and then we're going to have parentheses, and then inside of there, we could have something like this, t false. In which case this would say, well, if any of these are true, then this thing evaluates to true. If none of them are true, then this thing evaluates to false. And of course, inside of here, we could have expressions as well. So we might have something like this, and then an ampersand, and then here, t, f, Or is going to be handled very similarly to the AND case, because we have to get everything in between, and in between we might have comma separated values. And in theory, we could also just have a single value, I believe. Yeah, I guess based on this, we could just have a single value in here, which I guess in theory with OR, that would mean this is true and this is false. And then same thing with AND. So if this, we just had a single one, this is technically true. And if we had a false in here, this entire thing is technically false. Okay, so now how do we get into the implementation details? Let's consider an expression, an example. So let's say that we are given an expression that looks something like this. How do we solve it recursively? So we know this itself is one expression. So we can pass this in to our recursive function. Now, how are we going to pass something in? Probably rather than just passing like a string in or even a substring, because for example, like if we're here and okay, like this entire thing is an expression, and then we go through the list of expressions inside of there, we'll see, okay, this is one, and this is one. Rather than just taking like this substring and passing that in, that could be expensive. We're creating a copy and we'd have to figure out, well, where does this expression end? And to do that, like we might have nested parentheses in here. You can see how that's going to get complicated. So the easiest thing to do is just keep track of a pointer. So if we have our pointer here, let's call it I, and it's here. So this is the problem that we are currently at. And so to solve this problem, we know by reading the first character of this expression that it is an AND. So we know that with an expression, there's really only 4 possible cases. I guess technically 5. The easiest case would be where we're just given like the character t. This is the expression and this is where we're at. That's the base case. Same thing with false. That's another base case. So those are the 2 simple base cases. And then the 3 other cases, we have ampersand, we have or, and we have not. All of these expressions are going to start with that character followed by an opening parenthesis. Based on the criteria of the problem, like the description of the problem, we're guaranteed that that's going to be the case, like this and this. By reading the first character, we can figure out what to do. Right now we see it's an ampersand. Okay, so we know that the next character is going to be an open parenthesis. So what do we want to do in this case? Well, the easiest thing to do would just be say, okay, let's go inside the parentheses from here all the way to here, parse these and collect them into a list. So we know this is the base case, that's going to be true. We can take whatever this is, evaluate it, and then add it either as a true or false value. So you can see that that's kind of going to be the recursive case. In this case, I think that's going to evaluate to true, so we'd add that there. And then same thing with this, I think that's going to evaluate to true, but again, this would be another recursive case. So here, add true as well. I mentioned that these are subproblems, so we could call the helper function for these, solve that subproblem recursively, and then evaluate the result and add that result to a list. But the elegant thing is that we can actually do the exact same thing even with the base case. We don't care whether we have an expression to evaluate or if it's just a true or false character, because in theory, our helper function, our recursive function, should be able to parse the result of this as well. Because this is technically not true or false, it is a character, and we can recursively convert that character to what it actually evaluates true. And then once we collect all of those, suppose that this is a list of all trues, then given that we started with the ampersand, we can just take the logic and of all of these, and we know that that's going to evaluate to true in this case. If one of them was a false, then of course that wouldn't be the case. We would get false in the result. So now all of this probably makes sense to you. Conceptually, everything makes sense. The only tricky part is going to be maintaining that pointer I, because there's 2 ways to do it. We could pass that pointer into our helper function, but if our helper functions have different instances of that pointer, if they're not all sharing that pointer, and by pointer I mean index in this case, just in case somebody's confused by that, but if they're not all sharing that pointer, then we're going to run into trouble. We can still get a correct result, but it's not going to be efficient. We're going to end up with an n-squared approach, which isn't bad, but you can kind of tell just by looking at the input that this should be solvable in O of n time. Let me show you what I mean. Let me show you how we could end up with an inefficient approach by not sharing the pointer. We could end up with something like this. I start here, I see it's and, I increment that I pointer twice, so now I'm here. So this is like the first instance of the function. And then we're here, we might recursively call this. But in any case, like this is simple enough that we can increment our pointer by 1 or 2 to get to the next subproblem. But this is where things are going to get inefficient because, okay, now my pointer is here. I'm scanning through all of these, and this is the recursive case. So, okay, I'm going to recursively call this function. Let's say my pointer is still here. And now in this recursive function, I'm going to scan through all of these. I'm going to end my pointer somewhere over here at the end of that subproblem. And then I'm done. I evaluate all of this. It turns out to be true. And I return back to the parent. And now the parent's pointer, though, isn't all the way over here. It doesn't automatically just jump here because they're not sharing the pointer. So now from here, I have to increment all the way through. And let's say I end wherever the ending parenthesis is. That's fine, but you can see how this is repeated work. We already went through this section with the recursive case. The pointer already shifted through here. Now I'm doing that work again. It's not that big of a deal in this example, but let me show you an example where it would be a big deal. Imagine we have like and then a parenthesis, and then a parenthesis, and we just kind of keep going infinitely with parentheses like that. With this way, you can see how I'm going to start my pointer here. From here, I'm going to end up doing all that work. And then here, I'm going to do all that again and again and again. And now that I look at it, this actually might be less efficient than n squared. Let me just try to see if I can quickly figure it out. So let's say here we started and we go through here. Okay, then we're here. We're going to end up going through there. And then we're here. Well, it might be n squared. It might be less efficient than that. All I know is that this is definitely not linear time, and we can do better. We can eliminate that repeated work by having a shared pointer. So if in the recursive case, my pointer ended up shifting over here, I want this pointer to also have been shifted there as well. So that's just a code implementation detail, share the pointer. So now that we know that, we have the foundation to solve this optimally. So I'll just quickly dry run through it now. Let's say my pointer is here. I'm going to increment it by 1, regardless whether it's an ampersand or it's just a single character. We are always going to increment the pointer by 1 at the very least. Now, if it's this, or this, we're probably going to increment it twice. So now my pointer is here. Now I do this in a recursive call. I see that it's true, so I am going to return true, but I do want to increment the pointer because we're done with this subproblem now. So my pointer is going to end here. We found out that the result of this is true. We collect it inside of an array, and then we keep going. We probably want to skip the commas. They don't really do anything for us. So anytime we see a comma, we can just increment, and now we are here. And I don't even need to look at the character. As long as it's not a comma, I know it's either going to be a true, a false, this, that, or an ampersand. And so I can pass this index into my recursive call. Now in that recursive call, I'm going to see this, I'm going to increment it twice, and now I'm here, and now I'm going to loop once again. So I'm going to collect all of these into a separate array. And these are all primitives. So like this will return false, we'll increment it to be here, we'll skip this, we'll be here, it's false, we'll be here, skip it, here, we're true. So let's say we collected all of those into an array. It looks like this. And then we ended at the closing parenthesis. Now, conceptually, what should we do? When we're done with this entire subproblem, should we end at the parenthesis? It doesn't really make sense to do that conceptually, because if we're done with this subproblem, we want to start the pointer at the next subproblem, whether it's like a comma or something else, doesn't really matter, but we don't want to leave off at a closing parenthesis. So once we're done with one of those problems where you have to loop through it, we should probably increment the pointer one more time. And that works because think about it from the perspective of here. We started with the ampersand, we skipped the opening parenthesis, so now we're looping, and we want to stop looping once we reach the closing parenthesis. That's the only way we know that we can stop, when we reach the closing parenthesis. But we don't want to reach one of the inner closing parentheses, because that would be a false alarm. That would tell us we should stop when we shouldn't. There are still things left to process. That's why we never want to leave off at a closing parenthesis. So when we're done with this subproblem, increment one more time. Okay, so now that we have that, our pointer is over here. We collected all of these. We can evaluate this entire expression to be true. We can return true. And so now in the outer array, the array that belongs to this guy, we will have collected 1 true and 2 trues, and our pointer is now over here. Again, we skip the comma, we get to the not sign. So We pass this into the recursive function. We see it's a not, so we want to increment twice. We want to skip the opening parenthesis, and now we're here. We pass like all the values in this parentheses into the recursive, and since it's just a single one, this will return false. And then our pointer will have left off here. So this is telling us again, in this case where we started with a not, we don't want to leave off with a closing parenthesis. So let's increment that pointer one more time here. This will have been false, and then we negate that with this and turn it into a true. So basically that returns true, this returned true, and this returned true. So we collected 3 trues. Now that we're in the outermost recursive call, we ended our pointer here after the third subproblem. This tells us that we're actually done. This closing parenthesis belongs to this opening parenthesis, so we're actually done. So now we can take all the values that we collected into the array and them together, and that result will be true, so we can return true now. I think probably the hardest part about this problem is just knowing that you cannot leave the pointer at a closing parenthesis. When we're done with a subproblem, make sure that our pointer is not touching that subproblem anymore. So you can see that this way we scanned through the input once. That's linear time. In theory, due to the recursive call stack and just the fact that we're collecting these values inside of an array, the space is going to be linear time. The main bottleneck, though, is the recursive call stack, because if we had like a logic AND, we probably could have just ANDed these together as we went. But there's nothing we can do about the recursive call stack. We could theoretically solve this iteratively, but in that case, we would also need a stack. So depending on how nested this is, in the worst case, that would also be linear space. So let's code this up now. So the first thing I'm going to do is just rename this variable to s, just to make it easier to work with, to make this easier to code up. And then I'm going to declare a pointer I equals 0. And so this is very important because this pointer is going to be shared among all of the recursive functions. And I'm going to call this helper. And I'm actually not going to pass any parameters into this, because if I pass I into this, then we're creating a copy of that variable. But inside of the function, if I say non-local I, this is telling it use the I that's declared out there. So all of these recursive functions will share that. We could have alternatively made this like a member variable like this, self.I equals 0, and then we could have referenced it inside of here with self.I, but I think this is a bit more concise, so I'll do it this way. And to solve the problem, we will just return the result of the helper function. So now for the actual implementation, we'll start with the base cases. We could do this s of I is equal to true, return true. And we could do the same thing with false. If it's equal to f, return false. The problem with this is that if we have, let's say, an expression like this, not t or something like that, we don't want our pointer to leave here. If we're done with this part of the expression, our pointer shouldn't still be there. We want to increment the pointer before we return. So while we could do that in here, we could say increment that by 1, and we could say that here, increment that by 1. This is duplicate code, so it's easier just to take one of these and move them out. So that's exactly what I'm going to do. Out here, I'm going to increment the pointer. Now, the fact that we've incremented the pointer, though, referencing the character is going to be wrong. So here we would have to make this an I minus 1, and here we would have to make this an I minus 1. Rather than doing that, before we increment the pointer, let's just save the first character at the pointer. Let's call that C. Let's say s of I is C, and then we increment the pointer, and then here we can reference that character like this. And this is going to be useful because the first character is going to tell us what we do, whether it's true or false, or whether it's one of the other 3 characters, including not. So if C is equal to not, that we want to handle differently as well. So if C is equal to not, our I pointer currently must be at the opening parenthesis. So we should probably increment our pointer one more time before doing the recursive case, which would be just call the helper now. So there are multiple cases with the not. It could be a very simple case where we have something like this, not parenthesis and then false or true, or inside of here we could have another expression like this and then, you know, something like that, true, false. The beauty about the recursive approach is that this is going to be handled the exact same way as if we had this, because we can just call the helper function and it'll evaluate that subproblem and then return the result of that subproblem. Now you might think, okay, well then just call the subproblem and then return the result. That's fine, but remember what I talked about. The hardest part about this problem is knowing that you can't leave off at a closing parenthesis. So if you had something like this, whether it's like that, or if it was like a more complicated expression with an ampersand, this would still leave off at the closing parenthesis. Because yes, we returned false when we saw the f, but we only incremented the pointer once in that recursive call, so the pointer would have stayed here, but we want to increment it one more time before we actually return the result of that expression. What we can do is save the result of that expression in a variable like that, and then, yes, we can return it, but before you return it, make sure to increment the pointer one more time, like that. One thing you might notice I'm forgetting here is what do we want to do when we see the not operator? We don't just want to return the result of that subproblem, we want to negate the result of that subproblem. So don't forget to add the not if you're using Python, and if you're using other languages, you can just add this character. Okay, so these were the easy cases. These were the cases where we did not have to loop, but now we are going to have to loop. And remember, the only two other cases left are the and the or case. Before we get into either of those, they're going to be handled similarly. We want to collect the values. I'm going to call the array children. This is where we're going to collect the values. There's probably a better, name for this. But then we're going to start looping. Remember, the condition for looping is while the character is not the closing parenthesis. And before we start looping, we should probably increment one more time like this, I plus equal 1, for the same reason we did here, because we want to skip that opening parenthesis. And if you really wanted to, you could probably get rid of this line of code, and you could move this line of code outside of the if statement, like over here, but I don't think that would make this any more readable. It would probably make it less readable, so I'm not going to do that. But now, while we loop, there are really two cases. Either we arrive at a subproblem, suppose the example we're working with looks like this, and then I have like a true, a false, and then maybe I have another subproblem with like, say, an and then something more here. Either we'll arrive at this, or this, or this. All of those are subproblems. All of those can be handled recursively. So we can just say helper, and then we can take the result of that helper and append it to the children array, just like that. Now, the one case that we do want to skip is going to be when we see the comma. So as long as this is not a comma, as long as s of I is not equal to a comma, then we can recursively call this. Okay, so now again, the hardest part about this is the pointer. So let's make sure we have this part of the code correct. Let's think about it. If I call the helper function and it's on true, after that helper function, my pointer is going to be here, okay? If it's at the comma, we don't want to recursively call, but we probably do want to increment the pointer, so we can do I plus 1. And that'll work similarly here as well. What about here? From this subproblem, my pointer will not be left off here. It will actually be left off here, because when we're done with this subproblem, we increment the pointer one more time, and then we'll be here. But if I increment this one more time, I'm going to be out of bounds. I'm going to get an out of bounds error over here. So the only case where I would want to increment this by 1 is if it's equal to the comma character. So rather than just having this out here by itself, it should be guarded with an else case like that. Okay, now we're almost done. After we're done with this entire thing, we leave off at the closing parenthesis, but remember what I keep saying, we want to skip the closing parenthesis when we're done with that subproblem, just like we did over here. So I want to do the same thing when I'm done with this loop. So I'm going to have one more I plus 1 outside of the loop. So in the case of this subproblem, we would leave off here and we'd increment one more time after the loop, and then we'd be here, and then we recursively return back, and you know the story from there. Okay, so now we're almost done. We collected the children in here. So now it matters whether we're anding these together or oring these together. In either case, we actually saved the character up here. That character was not a true, it was not a false, it was not a not, so it was either and or. And so depending on which it is, if the character is equal to this, we'll handle it differently. And if it's equal to this, we'll handle it differently. You could loop over this array manually. We know there's going to be at least one value inside of that array based on the constraints of the problem. So you could initially set the result equal to something like this, children of 0, and then you could iterate over the rest of them. and then and them with the result, or them with the result, depending on either of these. But Python actually has a very, very nice built-in function to handle these cases, which is this, the all function. So it'll check if all of the values in that array are true. So we can just pass it in like this, and then we will return the result of that. Or if any of these are true, then we can call the any function like this. So another glorious day to be using Python. You can see this code is pretty long, but it's not, I would say, as difficult for how long it is. The main difficulty is the pointer manipulation and the fact that we are sharing a pointer among all of the recursive calls. So I'll go ahead and give this a run. Okay, a very, very sloppy mistake on my part. We want to keep going while this is not equal to the closing parenthesis. Really sorry about that. But now you can see that this code is correct. It's pretty efficient. If you found this helpful, check out Leetcode.io for a lot more. Thanks for watching, and I'll see you soon.